Okay, welcome back, Engineering 117. I took a look at the exam one average that is around 57. So I'm coming up with an extra credit opportunity right now. Okay, extra credit opportunity is related to quizzes. Okay, finish 5 quizzes. Okay, with a 100% grade. Remember, there are about 12 quizzes. So of the 12, you can take 10, you can take 9, but if you happen to get 5 of those quizzes with a 100% grade, then I will use that. Okay, I will use that to make up for exam 1. Okay, by the end of the semester, along with the homeworks, along with the final homeworks when they're due, one day before the final exam, if you have done at least 5 quizzes with a 100% grade, that will cover for a 100% of the exam 1. Okay, so that's an extra credit opportunity in case you want to boost your exam 1 grade. Any questions about that, please?
Just to make sure that I understood, that I'm understanding it correctly. You said 100% of the grade from the quizzes, right? Well, I mean,
There are 12 quizzes, right?
right, and
let's say you attempted 10.
okay.
On one you got 90, on one you got 80, one was 70, one was 100, 100, 100. So if you take 5 of the quizzes, doesn't matter which ones,
Right.
you get 100 on those, then I'll count those 5 towards your exam 1.
Like how is it counted towards the exam? Like for say the quiz is like 5 points, then you add 5 points to the exam grade, or
Yeah, each quiz is worth 20%, right? So if you were to take 5 quizzes, each is worth 20.
Okay.
So the condition is you have to do at least 5. You cannot do just one quiz with 100%. Come back to me and ask that it replace exam 1.
Okay.
Does that make sense?
Yep, got it. Thank you very much.
Yep. Other questions, please.
Can we, the quizzes, are we allowed to redo them, like the homework, until we get 100%? Because I think I've opened 1 or 2 just to kind of glance at it.
Right, that's fine. I can't let you take them more than once as a course policy, but that's the reason why you have 10 more quizzes. Let's say you open 2 quizzes already, but you have 10 more quizzes, out of which you only need to get 5 100% right. That's fair, right?
Yeah, I just need to go back and see which ones I've opened, because I think I opened, a couple of them just to glance at them because there were multiple attempts. But okay, I guess I'll look back and I'll see how many I have left.
Yeah.
Thank you for that.
Yep. Let's see something. The chat. Let's keep an eye on the chat. What's going on in the chat?
Sorry, question.
Yes.
How many attempts will we have for the for each quiz?
Each quiz will have 1 attempt.
Oh, okay.
Okay. Other questions, please.
Hey, Professor, I think just so we're all on the same page, I think there's some confusion. if you take 5 quizzes and you get 100% on each one, what would be your exam 1 score? Okay, good. Thank you.
Okay,
I just
does
wanted
that
to make
answer
sure.
your question?
Yeah, it does.
Let's say you took 12 quizzes, you took all the 12 quizzes, out of which you got 5 100% right. That will
Yep.
make your exam 100.
Okay.
Okay.
Thank you. Yeah, that
Yep.
clarifies it.
Okay. All right. Other questions, please. Any other questions, comments, concerns, feedback? Okay. Then what we are going to do is continue from here on. Um, we talk about new topic. Okay. First 2 weeks in this course was more about reviewing what you should have learned in your engineering 17, right? The complex power, and then chapters 9, phasor, chapters 10, so on and so forth. Transformers is one topic that you may not have learned in engineering 17, but we looked at that in this course. But the next 2 weeks is all about Laplace transforms. Okay, it is probably not likely that you have encountered this in your previous courses. Okay, let's see, the next exam, exam 2 is on 24th. And then we will probably have one of those review sessions the day before or a couple of days before. Okay, but if you look at the planned syllabus, we have Laplace transform and then application of Laplace transform. Okay, now Laplace transform is a technique, it's a tool, in some sense very similar to the phasor transform. See, in phasor transform, we were looking at the amplitude and angle, right? At phase angle. We were looking at the amplitude and phase angle. And then we were translating, we were working in between polar form and rectangular form, and then time domain. Okay, we were working, going back and forth between these 3 forms. The idea was this: if you are working with sinusoid waveforms, in time domain, it's not so easy to do the arithmetic, addition, subtraction, multiplication, division. It's not very straightforward to do sinusoid arithmetic in time domain. So we found out that a polar, okay, and a rectangular forms, equivalent forms exist. Okay, there is a domain, there's a world in which a complex number can be thought of as being very similar to a sine wave. Okay, a phasor can be thought of as being representative of a sinusoid waveform, and we saw that Euler's identity, e to the plus or minus j theta, is cosine theta. So there is some union. Okay, there is a marriage between the polar form, the rectangular form, and then the time domain is in the mix. Okay, we have seen that. But the purpose of doing all of that was to do the addition and subtraction in a rectangular form, and multiplication and division in polar form, so that the final answer can be converted easily into time domain. Okay, that was the idea. It's a tool, it's a technique. Okay, and the main drawback of this phasor transform is that it is available only to help us with steady state analysis. Okay, it cannot give us information about transient response. Okay, but the complete response is the sum of transient and steady state. Okay, now the Laplace transform that we are going to look at, that is in principle, in theory, in the spirit, very similar to the phasor transform, but it has more advantages. Okay, so it's the same idea as the phasor transform. So let's look at the characteristics of Laplace transform. Okay, the idea of Laplace transform, it's a very powerful technique. Okay, and it can help us with transient response. Where there is exponential, decaying exponential, so on and so forth. Okay, it can help us find the transient response. Okay, and then of course, circuits with more than one mesh or nodes in the equations. If there are more than one mesh and node equations, each with their own derivatives and integrals. Remember, L di by dt, C dv by dt. If you have to, so V in an inductor is L di by dt. I in a capacitance is C dv by dt. Now, if you want to get the V in a capacitance, you have to do the integral of current. So if you were to set up equations for circuits that have resistors, inductors, and capacitors, okay, then you may have to end up doing derivative and integral equations when you write node equations, mesh currents, node voltage equations using inductors, capacitors, and resistance, all of these elements, then our time domain equations will have integrals, will have derivatives, so on and so forth. Okay, so this is a pain. This is exactly where Laplace transform helps. Okay, Laplace transform provides for a very, very clean and efficient methodology, ease of analysis. Okay, by converting the integrals and derivatives in the time domain to algebraic equations, so on and so forth. Okay, so in other words, if you had integral differential equations, some function 1 of t plus d by dx of function 2 of t plus d squared by dt squared of function 3 of t, all of that equals to 0. If you had a complicated looking differential, integral differential equation in the time domain, instead of messing with this in the time domain, if we were to transform it to the Laplace domain or the frequency domain, what we would get is an equation. An algebraic equation that is much easier to deal with. Okay, that's the idea. The same idea of a phasor transform. It's very difficult to do addition, multiplication, arithmetic operations on time sinusoid forms in their time domain. So you convert it into a different form. Even so, Laplace transform essentially transforms complicated derivative time domain equations into simpler algebraic equations in S squared and S cubed in frequency domain. Everybody with me? Questions, please. Questions so far? Okay. So what we are going to do is to now define the Laplace transform. Okay. Let's look at the 12. That's a little bit of introduction of Laplace transform. So definition. So again, before we go into the definition, I want you to park towards the back of your mind that at the end of the day, Laplace transform is a technique. It's a tool. It's meant to make our life easy. Okay. If you're struggling with the Laplace transform, it could be for two reasons. One reason is that you are seeing it for the first time. It's still so fresh that you still not have put a handle on it. The second thing is you probably are not doing it right. Do enough problems, do enough practice problems. You will begin to see how intuitively you can solve these problems and use this technique to make our life easy. Okay, so that's the goal. Using Laplace transform or any other technique, we want to make sure that we are making our life easy. Okay, so here it is. Let's say I have a function in time domain, some function t, does not matter what function it is. Any function in time domain, if you were to integrate it from 0 to infinity, okay, in this fashion, e to the minus st dt, this is called the Laplace transform of the function of t. Okay, the function of t, the Laplace transform of it, that's the symbol. Okay, italic L is defined. When you see this t equals to sign, that's by definition, that's the definition. Okay, and then we also represent it using f of s, where s is a variable in the frequency domain. Okay, there's nothing crazy about it. Nothing. We don't have to you know, lose our sleep over this. You're just taking a function, multiplying it with some exponential, and then integrating it. When you do this transform, when you do this operation, it's called a Laplace transform. Okay, the one intuition that we want to preserve is about this guy. Okay, if you think about it, e to the negative st is one organic entity. So the exponent st should have no units, meaning that if t is in the time units, s should be in 1 over time or in the frequency domain. Okay, when you hear people say that you're transforming from time domain to frequency domain, or when you hear people say that S is the frequency domain variable, what it simply means is it's the inverse or the reciprocal equivalent of time, right? Because it comes from the fact that e to the power, that power should have no units. Because that should have no units, S should balance out T by being the reciprocal. Reciprocal of time is frequency. Hence, we are translating. So let me write it out here, translating from time domain to frequency domain. Okay, so your result, your answer is going to be in a variable S that has units of frequency. Okay. Now, so what we do here is the general procedure. Okay, any circuit that we want to analyze. Okay, if we want to analyze a circuit, what we do for a circuit or for a waveform or anything that we want to analyze, we write its equation in time domain, then take the Laplace transform. Once we take the Laplace transform, it's going to be in much simpler S domain equation. Okay, whereas you would find integrals and derivatives in the time domain equation, once you take the Laplace transform, they are going to appear as algebraic equations. Then you would solve them. Okay, then you would inverse transform, go back to time domain. Okay, this scheme is very, very familiar to us. Okay, so time domain to polar form to rectangular form, then you go back to polar form and eventually express in time domain. You do the meat of your calculations in this domain. Not just that, okay? We live in an analog world, okay? So when we speak into a microphone, I'm providing an example of translating between different domains. The analog signal is converted into a purely digital signal. Okay, it's translated into a digital world. Okay, this is where microprocessors, microcontrollers, they do a lot of signal processing. So when I'm speaking into a microphone, that analog signal is being converted into a digital domain. All the filtering, all the um, signal processing is done in the digital domain. It is communicated in the digital domain. And on the other end, when you're receiving it through your earphone, that is translated back into the analog domain. Okay, this is in spirit, similar to what we do in the different transforms. Okay, um, real world is in one domain, your convenience is in a different domain. So you conveniently manipulate in a different domain and translate back to the real world domain. Okay. Questions so far, please. So there's not a whole lot we discussed here. I just tried to provide some intuition and some common sense idea as to the reason for doing this. Okay. So I'm going to provide some examples. Okay, there are two tables, 12.1 and 12.2 tables that provide a detailed description of a detailed list of the different types of waveforms and their Laplace transforms. We'll come back to that in a second. Okay, but as a representative, let's look at a step function. Okay, a step function and how we do the Laplace transform of it, and then how we can use it in circuit analysis. Step function is very useful in our circuit analysis, so we are going to look at that. Okay, so what is a step function? And it's a very simple business. All it is something, anything, any signal that turns on, that's off, followed by on. Okay, here the green signal, that's the function that's shown as a function of time. Okay, let me see if I can put it in a different color. Okay, there. Okay, on the x-axis is time, and on the y-axis is a function. Okay, so any phenomenon, any signal that is initially off. Okay, let me see if I can style it in much bigger. Okay, bolder. Okay, so this green signal, maybe I got to put it back in. I don't want this to be a bit of a distraction. Okay, so the signal is the green signal. Okay, that guy is called a step function. Okay, if its value is k, then we call it, it's not a unit step function, but you get the idea, right? Any signal that is off. So the mathematical definition of it, okay, if I were to look at the mathematical definition of, and the symbol for this is k u of t. That's the symbol for step function. Okay, now the mathematical definition of step function is k u of t, the step function, equals to 0 when t less than 0. Okay, k u of t, that's the step function, equals to k for t greater than 0. Everybody with me? Simple, right? So for time to the left of the um, time 0, the value of this function is 0, and towards the right, it has a constant value of k. Okay, there are many signals like this. If you turn a switch on, its value initially is 0, then its value is a constant k. There are many signals that are like this. Okay, so it's a fairly representative step function. So question for you. Did you see anything missing here in the definition? Look at the definition of the unit step function. What is missing in the definition? K equals to 1. Sure, if the value of Keras is k when k equals to 1, so let me write it out here in a different color. When k equals to 1, we call this a unit step function. Okay, sure. But look at the definition, these two lines, and ask yourself the question, 0 itself, right? Ethan says 0 itself. What is the value of k u of t when t equals to 0? Ethan, you're right. Okay, that's where it is undefined. Okay, when k equals to 0, that's called a discontinuity. Okay, k u of t is not defined for t equals to 0. Okay, that's the definition of the signal. We cannot determine what its value is. Sometimes when it is necessary, we assume k u of t equals to a half of k at t equals to 0, just so we can solve the problem, not because that is its value. Okay, but because we have to have a way of solving the problem, and this seems to lead us to the solution. So we are okay occasionally to assume that its value is 0.5 at t equals to 0. That's an arbitrary assumption. That's a weird assumption, but that's a not a big problem for us. Okay, we can get around it. Let's see. Let's look at a few variations of this. Okay, let's look at let me first copy this step signal, right? This is a step signal that indeed does look like a step. Okay, it does look like a step. And the step or discontinuity, let me give you the name for this guy. This guy is called a discontinuity. At t equals to 0, there is a discontinuity. Okay, we don't know the value of the signal at t equals to 0. Now let's put a, so this is the step function. Okay, let's see if we can take this guy and modify this a little bit, put some spin on it. Okay, let's say I have a function that's simply translated in time. Oops. Okay, that's simply translated in time. Okay, everything is exactly the same except that this damn discontinuity. Okay, that guy, that step, that transition from off to on. Earlier it was happening at t equals to 0. Now that transition from 0 to 1 or 0 to k happens at t equals to a. Okay, then the function is not k u of t, then this function is k u of t minus a. Okay, it's a delayed function. Okay, instead of turning on at 0, it has to turn on after some a time. Okay, so this is a delayed function. If the discontinuity occurs towards the left, or in other words, if this step up occurs towards the left of origin, then this would become a plus. Okay, you see the idea. So the first spin that we are going to look at is if it is translated, if the step transition is translated left and right. Okay, now the next spin is simply, it could be delayed or let's copy this and a different version of okay, a different version of the step signal. Okay, what is the difference here? What difference do we see? Is it a simple difference? Is it a big difference? Straightforward? What's the difference between the step signal on the top and the steps? It's reverse. Ethan, thank you. Instead of going from off state to on state, it's going from on to off. Okay, it's going from on to off, right? So the definition of this, the expression for this is simply k u of a minus t. Okay, everybody with me? So these are different kinds of step signals. Mathematical definition of some signal that is turning on and off and on. Okay, that's all there is to it. And it becomes, it turns out to be a very important function. Okay, one of the basic functions that we will study here. One of the basic signals that we will study, the step signal. Let me see if I can move this up a little bit. Okay, that's the step signal. Now, most homework problems are centered around the step function to represent signal of finite duration. Okay, so here is the idea. If I had a signal that looked like this, somehow, let's say I had a signal that looked like this. Okay, how do I represent this using step functions? Okay, so let me put some axes around it. Let me first do this. So we looked at the step function just now, something that's off and on and off. It could be translated in time, so on and so forth. Now what we are going to do is to use step functions to represent waveforms of signals of finite duration. Okay, let me see if I can put some axes around it using this color. Okay, let's see. That's the x-axis. Okay, that's the y-axis. Okay, y-axis is time, x-axis is signal, and I can even put some numbers on this. Let's say this is 1, 2, this guy is 3, this guy is 4. It seems the signal of interest to me, this sawtooth signal, okay, this one is going up, it's only existent between 0 and 4 seconds. Okay, the rest of the time it is absent. Okay, now what we are going to do is to see if we can represent this signal using step functions. Okay, so here is what we are going to do. Everybody with me so far? We looked at some function that looks like this, some signal that looks like this, and we are trying to represent that using step functions. Okay, the first thing we do is notice that there are 4 parts to this, 4 or 5. Let's see. There is one part. There's a line, a piece. It's a piecewise linear. That is what it is called. Okay. There's a that's the first part of the signal. Then there is a ramp that's going up. Okay, that part of the signal. Then there is this straight line that seems to be falling down. Okay. Then there is this guy that seems to be raising up as well. Okay. Then of course there is this flat line that's constant. Okay. So there's 1, 2, 3, 4, 5 parts to this waveform. Okay. This is what we call a piecewise linear. Okay. From 0 to 1, it's a straight line. From 1 to 3, it's a straight line with a negative slope. From 3 to 4, that's another racing straight line. And that's so it's this complete signal is made up of pieces of linear signals. Okay, let's see how we can represent this using a bunch of step functions. First of all, let me give you the definition for the definition for this signal, right? So if this is f of t is 0 for t less than 0. Okay. Similarly, f of t equals to 2 times of t if this were 2, okay, and this were 3, okay, this was 3. Now its value though is negative 2. Okay. Now let's see, for t in between, you see, when the time is in between 0 and 1 seconds, okay, 0 and 1 seconds, it's a straight line, 0 less than or equals to t less than or equals to 1 second. Okay, that corresponds to this yellow part of the wave. Okay, now this corresponds to the, let me color code this differently using, I don't know, a green signal. Okay, so t less than 0 corresponds to the green part of the wave. Okay, then between t equals to 1 and t equals to 3, it corresponds to the orange signal. So we are looking at the definition, negative 2t plus 4 for 1 less than or equals to t less than or equals to 3 seconds. Okay, so that corresponds to the orange segment of the wave. Okay, let me see if I can make some room here. Everybody with me? Then there is 2t minus 8 for t in between 3 and 4 seconds. That corresponds to the purple part of the wave. Okay, that's between 3 and 4 seconds, right? Now this guy between 1 and 3 seconds, that's this guy. Okay, of course there is a yellow waveform here, so it's color coded in the sense that the different times and segments are representative of are represented using different colors. Okay, then of course, what's the value for t greater than or equals to 0? What's the value of the signal for t greater than or equals to 4? Okay, when the t time is greater than 4, what's the value of the signal? Everybody with me? Did I miss everybody? Did I miss anybody? Okay, when you go past t equals to 4 on the x-axis, what is the value of the function? It's 0, right? Correct. Right, Ethan, you're right, it's 0. Okay, so here is the definition. Here is the time versus value relationship for the function. Okay, clearly this is piecewise linear. One part of this is a straight line. Okay, the other part of this is a different straight line. Okay, and then the other part of this is another straight line, and the rest are all horizontal lines. Okay, so what I'm looking at is the definition of a signal that is piecewise linear. And so far, we have not used the step function. What we are going to do here on out is to use step function to integrate, or I mean, not to put together, let's not use the term integrate, to put together these definitions into a single expression, okay, by turning on or off. Okay, here is the deal. Okay, I'm going to start with this. Okay, look at that definition. Okay, if you look at that definition, it says this 2t is off before 0 and off after 1. So this is what I'm going to do. Okay, you see carefully, 2t, this wave 2t is on between 0 and 1. You with me? So all I have done is this 2t is the signal that's going up. Okay, that's the only highlighted signal here. That's the yellow signal. That's the line that turns on. Okay, that turns on at t equals to 0. Okay, and this guy turns off. Okay, at t equals to 1. Okay, let me do that for the next sign as well, next signal as well. So f of t is this guy plus, now there's a second wave, a second line, this guy that's turning on at t equals to 2. Okay, and it is on, it stays on until t equals to 3 and turns off at t equals to 3. So this wave, negative 2t plus 4, is ut minus 1, turning on at t equals to 1, minus u t minus 3. Everybody with me? Questions, please. Okay, so that takes care of the orange term here. Oops, that takes care of the orange term here. Okay, earlier I had the yellow signal. What else do I have to account for? The purple wave. So could somebody tell me how to incorporate this purple signal here into this equation? How did I get plus 4 and minus 8? Yes, I'll talk about that in 1 second. For now, please bear with me. Please trust me on that. Okay, I'll come back to that in 1 second. Now, how would you account for the purple wave? The purple wave is this guy, right? That is turning on at t equals to 0, at t equals to 3, and turning off at t equals to 4, right? So the way I incorporate that is, this purple wave has an equation of 2t minus 8. Okay, that's the equation 2t minus 8. Okay, and you turn it on when t equals to 3, and this minus means turning off, and you want to turn it off. Thank you. 2t minus 8 into ut minus 3 minus t minus 4. Correct. Oops. So that corresponds to the purple wave. Okay, so if you look at the waveform on the top, it's a piecewise linear waveform. Now, what I have done is to assemble that into one definition that is turning this line on and off, this guy on and off. So all we are doing is using a step function. Okay. Questions, please. Questions so far. And I like that Ethan has a question about how we got this t plus 2 and t minus 3. Okay. Let's see. Let me copy this one more time here. Okay. Everybody with me? So this is one single. You can simplify this in terms of e, t minus 2, t minus 1, all of that. And then you can rearrange this, but you get the idea. What we are using is all of this is a step function that is on, and this is a step function that is turning it off. Okay, that is turning the line off. Okay, now here is the deal. Let me copy this guy and see how I got the equations for this. Okay, let me clear up all of this. Okay, okay, let's see. There is one piece, the definition of that is f of x equals to 0, right? Any value of f of x equals to 0. Now, any value of t doesn't matter. If it is below 0, the value of the function is going to be 0, right? How about this guy, which is, that's a straight line, right? So when we want to write the equation of a straight line, we use this equation, y equals to mx plus c. We use the same equation to find the definition for that guy. We use the same equation to find the definition for this guy. And we use the same equation to find the definition for this guy. Okay. So this value is, if you were to plot it on the y-axis, that would be -2. Okay. So we are using the straight line form y equals to mx plus c to determine the expression for the orange wave, y equals to mx plus c. Okay. And then if you look at this value is 1. So this point, this coordinate, that point has coordinates of x value is 1 and y value is 2. Okay. Now, this is, of course, origin. Okay. That is, of course, origin that has coordinates of 0, 0. Okay. Now, using these 2 points, 0, 0, and 1, 2, we should be able to find a straight line that passes between these 2 points. Okay. The first thing I want to do is to plug in a value of x equals to 0 and y equals to 0. So 0 equals to m times 0 plus c, which implies c value is 0. Okay. Then I find the slope value. Okay. There are a bunch of ways in which I can find slope. M equals to y2 minus y1 by x2 minus x1. Okay. That's an equation for calculating slope. Okay. In this case, y2 is 2 minus 0 by x2 minus 0. So this is x2 y2. This is x1 y1. Okay. Now we have a value of c equals to 0. We have a value of m equals to 2. Therefore, y equals to mx plus c means y equals to 2t. Okay, because the value of m is 2. Okay, and then this y is of course a function of t. Okay, everybody with me? So that is where I got this guy from, this 2t. Where do you think I got that 2t from? I simply got it by plugging in the value of m and c. Okay, let's look at the other line. Okay, the other line, this guy, I don't know what color I used there. This line highlighted in orange. Okay, let me clear this out. This line, okay, that is falling 1, 2, and that is passing through this guy. Okay, 2, 0, right? The x coordinate is 2 at that point, and the y coordinate is 0. Everybody with me? Okay, 2 and 0. So now what I'm going to do is to find the orange line. Okay, I take these 2 points, 1, 2, and 2, 0. Okay, let me show you how I find the expression. Find y equals to mx plus c. It's a straight line. What's a straight line that passes to 1, that passes through 1, 2 and 2, 0. So this is x1, y1, and this is x2, y2. What is the straight line that passes through these 2 points? Well, we can start by doing y equals to mx plus c. Okay, and then let's start by finding m. The definition of m, or the slope, is the change in y by the change in x. Okay, the slope is the difference between the y coordinates over the x coordinate. What would that be? That is 0 minus 2 divided by 2 minus 1. Okay, so my slope comes out to be -2. Once I have this slope -2, I'm going to go back to y equals to mx plus c. In this case, x is t, because the x-axis is time variable, plus c. And you can plug in any number, 1, 2, or you can plug in 2, 0 in there. Okay, I know for a fact that m value is just -2. Okay, so let's try to plug in the point 2, 0. Okay, meaning that when I have a value of t equals to 2 and y equals to 0, okay, I should get a value for c here, 4, meaning that m equals to -2, c equals to 4. If I go back to y equals to mx plus c form, I have the function to be -2t plus 4. Okay, so it's nothing but the equation for a straight line. Negative, sure enough, that is what I used, -2t plus 4. Where do you think I got that from? That's a straight line equation. Everybody with me? Ethan, does that answer your question? Yes. So if you see this problem again in the homeworks, what you're going to do is any piecewise linear function, And there are many variations of this. Doesn't matter. If there are a bunch of straight lines, all you got to do is look at 2 points. Okay, look at 2 points, point 1, x2, y2 for this straight line. Okay, express it as y equals to mx plus c. You can calculate the slope. You can calculate the y-intercept using just these 2 points, meaning that if you have 2 points, that is enough to give the expression for the straight line. Okay. Now, I'm not going to show you explicitly where I got this -8, but you should be able to see. Okay, but I will point out some quick sanity checks that you can use though. Okay, let me not erase this actually. Pay attention to the purple equation. Okay, it seems to have 2t minus 8, mx minus c, something of the form. The m corresponding to the t is positive, right? The slope is positive, and sure enough, you go back and take a look at the purple wave. That seems to be raising. When you go from, when you increase the value of t, the value of y seems to be increasing. Okay, that's a positive slope. Okay, how about this guy, the orange guy? That has an equation of -2t plus 4. The slope seems to be negative, and it is slanting backwards. As you increase the value of time, the value of y is falling down. That's a negative slope. Okay, you get the idea. So by looking at the value of the slope or the magnitude of the slope, if it is negative or positive, you should be able to do a sanity check and verify that your waveform is either slanting up or if it is slanting down. Okay. Now, if you have a sine wave, I'm probably not going to spend a whole lot of time now. If you have a sine wave that looks like A, that's A, not pi, okay? A sine 2 pi t, okay? And then at t equals to 0, it is off. At t equals to 0, it begins to turn on. And at some t equals to A, it goes back to 0 again. Okay, then what you can do is you take this sine wave, okay, and you want to express it using step signals. You turn it on at t equals to 0 and turn it off at t equals to A. So any signal that is turned on and turned off at specific times, that can be represented using step signals. Okay. Now, if you go back, what did I say about step signals? We can use step functions to represent signals of finite duration. If they have a finite duration, I can use step signals to turn them on and turn them off. Okay. So that step signal being used to turn on and turn off. Okay. Let's see what else we got. Okay. If there's another signal, maybe I will not write it out. I will probably just show it here. Okay. If you have a signal that looks like this, so problem 12.1b, for example, if you have a signal that's looking like so, okay, let me clear off all the highlights. Okay, it's another piecewise linear signal. Okay, then based on the definition, you can set up the different piecewise linear functions. You can calculate the slope. You can calculate the y-intercept for each of these signals, and then you can turn it on and turn it off, turn it on, turn it off, so on and so forth. Get the idea? So if there is a sine wave that's turning on and off, you can do the same thing as well. If you have a piecewise linear wave that is turning on and off, you can represent it using step functions as well. Okay. So we looked at how many examples did we look at? We looked at 3 examples. Example 1 is using step function to this kind of sawtooth wave. Another example is a sine wave. And of course, the third example is that that wave that I showed you earlier. Okay. Questions, please. What questions do you have? So maybe I can introduce a different signal as well. It's 5:15. Maybe I have a little bit of time to indicate impulse function. Okay. So far we looked at definition of, so 12.1 is definition of Laplace transform. Laplace transform. So if I had a function f of t, then multiplying it with e to the minus st, integral 0 to infinity dt. This transform is called, this operation is called the Laplace transform. Okay, that's what we looked at. We did not look at examples for implementing this yet. Okay, this is also represented as f of s. That's the Laplace definition. Then in 12.2, we looked at step function. That is off until t equals to a, and then it is on at t equals to a and later on. Okay, so k u of t minus a was the unit step. That's the step function. K equals to 1, we call it unit step function. So this is what we looked at so far. 12.3, I'm going to talk about impulse function. Okay, impulse function. It's a new kind of a function that we will encounter often. Okay, let's see. Okay, that's my time axis. This is my function axis. Okay, so now unit impulse function is a very interesting function in the sense that it exists only at one instant of time. Okay, at t, oops, at t equals to, at that instant, only at that instant, this function exists, delta t exists. Okay, so it has, you can call it, the definition of it is, so this is the definition of, okay, the impulse function has an infinite magnitude for 0 duration. Okay, they, of course, this kind of waves do not exist in in nature, in real world. Okay, this kind of a momentary signal does not exist in real world, but what exists is something similar to that. Okay, something that very closely approximates this kind of behavior. Okay, that is only momentarily on. Okay, that's momentarily on, is called, that exists. Okay, there is a, you can derive this impulse function as a derivative of, the textbook talks about, if you had a discontinuity. Okay, if you had a discontinuity that we showed earlier, right? A step function had a discontinuity. If there's a discontinuity, and if you were to zoom in onto the discontinuity, okay, and assume that this discontinuity has a linear profile, then you can do the derivative of this. Refer to the textbook to a more formal definition of that. Okay, of course, Professor Tetro's slides provide more formal introduction as well, right? That's not what I'm interested in. I just want to present to you this delta function that has some value. Okay, this delta function has a value only at an instant of time. At the rest of the times, its value is 0. Okay, so the textbook says that if you were to do a derivative of the discontinuity of the step function around the discontinuity, you get a and make that epsilon very small, it becomes an impulse function. But mathematically speaking, the area, okay, under this guy, under this function, delta function, dt, okay, if this was not a unit delta function, but its value is k, okay, if it's k, the mathematical definition of that is that the area under this curve is constant k, okay? And when delta t equals to 0, t equals to 0, area under the impulse curve, okay? Now, by the same token, as we discussed earlier, if the impulse is occurring not at origin, but at a later time at t equals to a, then we call it a delta function at t minus a. Okay, so don't get lost. There are two kinds of signals that we have looked at so far. One signal that is off before it is on. Okay, that's called a step function. And that's not a very imaginative name, and thankfully so. It's a straightforward name because this is a step signal. This steps from off to on. Then there is a signal that is just present at an instant, at one instant of time. This is called an impulse. Okay, this is called an impulse function. So one kind of function is step, the other kind of function is an impulse function, delta t. This is u of t. Okay, so that's what we looked at. If this is shifted to the right or to the left, based on that, you can have a t minus a or t plus a. Okay, so if this were not a unit impulse function, you have a k times delta t minus a. Okay, k times delta t minus a. So impulse function and step function. Okay, the use of impulse function really is in shifting. It's not shifting. Okay, rather I mean shifting. What does that mean? If I had a waveform some waveform, doesn't matter what kind of waveform I have, some function chi, it doesn't matter. Let's use some g of t as an arbitrary function, okay? And if at t equals to some time a, okay, I multiply that function, okay, by an impulse function. This is an impulse function, right? So the definition, so one of the properties of impulse functions is the area of g of t multiplied by delta of t minus a is f of a, okay? I will, let me define that in plain English, okay? What it means is, if I have any waveform, g of t, and I multiply that by the impulse function, okay, then what we are doing is, we are simply retrieving the value of the function at that instant of time, okay? So in other words, let's say I have a function that looks like this, and you're interested in finding out what its value is at that instant of time, right? At that instant of time, when t equals to, I don't know, 7 seconds, then what you would do is take g of t, the function, and multiply it by the impulse at that instant of time. That will give you the value of g at 7, okay? Multiply that and of course integrate it, find the area of the curve. So what it really means is, if you want to, what is the value of g of t at t equals to 7, then what you can do is you can use this shifting property, multiply it with delta t minus a. That will give you the value of g of 7, or g of t at t equals to 7. It's called shifting because of this waveform, everything else is ignored and only its value at t of 7 is selected. Everything else is sieved away, sifted away. Okay, so simply speaking, step function, then there is the impulse function. Okay, of course, we looked at the shifting property of delta function or the impulse function. Okay. Questions, please. What questions do you have? Okay. That's the shifting property of delta function. What else we got? Now, we have a bit of time, so let me throw in a few Laplace transforms here. So refer to table 12.1 and 12.2. Maybe I will show them to you. But the idea is, if you take a delta unit impulse function and do the Laplace transform of it, Okay, or in other words, take the unit impulse function e to the minus st integral 0 to infinity dt. If you do that, you will see that the area under this curve, or the Laplace transform of this guy, is 1. Okay, now the Laplace transform of the derivative of this impulse function is s. Okay, and the Laplace transform of the nth derivative is s to the n. So it's just a matter of remembering these Laplace transforms. You don't even have to remember. Let me give you some functional transforms here. Okay, functional. The textbook talks about functional transforms. What it simply means, a function f of t and its corresponding Laplace transform. Okay, if you had a delta function, I mentioned that its Laplace transform is 1. Similarly, if you had a unit step function, then its Laplace transform is 1 over s. Okay, and I'll show you the Professor Tetros videos show you how one leads to the Laplace transform of the other. Okay, if you were to take t, okay, and take the Laplace transform of it, you will get 1 over s squared. Okay, that's an easy thing. That's a straightforward thing to demonstrate. Start with, this is your function, right? T. Then if you multiply it with e to the minus st and integrate it with 0 to infinity dt, and then do this integral, you'll see that its answer is 1 over s squared. Okay. Now, let me throw in a few more definitions. E to the negative at, the Laplace transform of that is 1 over s plus a. Okay. Similarly, sine omega t, the Laplace transform of that is omega by s squared plus a squared. Okay. Refer to the homework problems and refer to Professor Tetros videos on how I got this. Okay, but this is again on this is on table 12. This is 12.1 actually. Okay, so you don't have to memorize this. You just want to have them handy for your exam, and you should be able to use them. Okay, after a little bit of practice, you will begin to see how we can use them conveniently. Cosine omega t, the Laplace transform of that is s by s squared plus omega squared. And we are going to look at some example problems in the next class. Okay, for now, please bear with me. If there is a t e to the negative at, the Laplace transform of that is 1 by s plus a, the whole squared. In the couple of minutes that I have left, maybe let me see if this guy has some there are some functional and some manipulation Laplace transforms here, but not all. Okay, if you look at table 12.1, okay, look at table 12.1, or maybe let's just see this guy on Moodle. If you look at the chapter 12, okay, Maybe the table is right here somewhere. There are several examples here. Now let's see. I'm looking for a particular table. This guy. Okay. I'm looking for this table that lists a function and its Laplace transform. E to the negative at cosine omega t is s plus a by s plus a whole squared plus omega squared, that kind of thing. So a list of frequently used functions and their corresponding Laplace transforms. Okay, when we come back, we look at table 12.2 and then operational transforms, and then we will look at some examples as well. Okay, questions, please.